Hi everyone. In this video, we're going to take a look at another test to determine convergence or divergence of series. And in this lesson, we're going to look at the ratio test. And then in another video, we will consider the nth root test. Now, both of these tests can be used when some of our other tests, like the integral test or the p-series test or the domination test, aren't appropriate or would be difficult to use. So first of all, let's consider the ratio test. Now the ratio test makes this statement. We start out with a series involving the terms a sub n, and we assume that these an terms are non-zero. And then we consider this limit as n approaches infinity. So we consider the limit as n goes to infinity of the a sub n plus 1 term divided by the an term, and we take the absolute value of that quantity. So this is just the limit of the an plus first term divided by the previous term in your an sequence. Take the absolute value of it. Now let's suppose that that limit is equal to rho. That's the Greek symbol rho. Then we have the following three conditions that will determine whether or not this series converges or diverges. So case 1, if that rho is less than 1, then your series converges absolutely, which means that the series converges as well as the series of the absolute value of the an terms converges as well. So both of these series converge. That's a little bit stronger than saying just the an series converges. You're also saying the series of the absolute value of the an's converge. We also have this case. On the other hand, if the rho is bigger than 1 or rho is equal to infinity, then the series diverges. Then our third case is if the rho is equal to 1, well, in that case, the test fails. So this test doesn't work. The series may converge or it may diverge. You have to use some other test to determine if you have convergence or divergence then. Now let's take a look at a few examples that will clarify this test. So for this example, we want to determine if the series of 5 to the n divided by n factorial converges or diverges. So to apply the ratio test, in this case the an's are equal to 5 to the n over n factorial, and a sub n plus 1, that's just going to be 5 to the n plus 1 divided by n plus 1 factorial. Okay. So now if we look at the limit as n goes to infinity of an plus 1 over an, well, in this case that's going to be all right, there we go. Now we can simplify this by flipping the denominator up and multiplying it against the numerator, and what we get is and now we can further simplify this. Notice 5 to the n plus 1 over 5 to the n. These will both cancel and just leave us with a 5 up here in the numerator. Now also n factorial divided by n plus 1 factorial, these are going to cancel and just leave us with an n plus 1 in the denominator. Recall, for example, if we look at 4 factorial divided by 5 factorial, right, that's going to be 1/5, right? Because the 5 factorial you can think of as 4 factorial times 5, right? And so the 4 factorials would cancel, leaving you 1/5. So this will cancel with this, leaving just an n plus 1 in the denominator. And so what we finally get is the limit and there we go. So that's what the limit of the a sub n plus 1 over a n terms is equal to. It's the limit of this quantity, and of course that is equal to 0. So that is our rho, and since that is less than 1, we have that the original series converges, right? We are in case 1 now. So therefore this series converges because the rho is less than 1. And there you go. That's how you employ the ratio test. You just have to look at the limit of this quantity and then see which case you fall into. Let's take a look at another example. Let's consider this one. So we want to look at the sum from 1 to infinity of n squared plus 1 divided by 2 to the nth power. So in this case, these are the an terms. And so if we look at okay, so there's an plus 1, that's this, divided by an. Now we just need to simplify this. Once again, let's flip that up and multiply it against the numerator, and what we get is this. And now simplifying this, you see the 2n here and the 2 to the n plus 1 here. These will cancel with each other, leaving us with just a 2 in that denominator there. And then we're going to have these two polynomials, and so let's write this as and there we go. Now, this is a second degree polynomial divided by another second degree polynomial, right? Now, the leading term in this polynomial is going to be n squared, right? If we were to FOIL this out, we would get n squared plus 2n plus 1. In fact, let's just write that out down here. So we're going to get and so you see this part is going to approach 1 as n goes to infinity because the degree of the polynomials are the same. So the limit of this term is going to be the quotient of the leading coefficients, which are 1 and 1. And so this is going to 1. And this, of course, stays at 1/2. And so our limit is just going to be 1/2. So this will equal 1/2, and that is our rho. Okay, so we see that our rho is less than 1, so we're in case 1 again, and so therefore we can conclude that this series converges. There we go. And once again, that's because we found out for this limit it was equal to 1/2, and that was our rho, which is less than 1. Okay, so we were in case 1 again. Now let's take a look at this one. So here we want to determine if the summation of n factorial over n to the 8th plus 1 converges or diverges. So in this case, these are going to be our ANs. And so once again, we just need to look at and so just evaluating this, we get there we go. And now once again simplifying this just by taking the term in the denominator, flipping it, multiplying it against the term in the numerator, we end up with this. And there we go. Now, the n plus 1 factorial divided by n factorial, these are going to cancel and leave us with just an n plus 1 in the numerator, right? Because n plus 1 factorial divided by n factorial is n plus 1. And then we have these two polynomials here, so let's write this as and there we go. Now, if you were to FOIL this out, that would be a lot of work, but this is going to be a polynomial of degree 8, and its leading term is going to be n to the 8th power, plus lower order terms. And in the numerator, we also have n to the 8th, so this quantity is going to be approaching 1 as n goes to infinity. But then we have this n plus 1 right here. That's going to be approaching infinity, of course, as n goes to infinity. And so our answer here is infinity. And so we see that we are now in case 2. So the rho is equal to infinity in this case. That's our rho. And so therefore this series diverges. And there you go. And you should have a feeling that this does diverge because, as we've seen before, you have a factorial in the numerator and only an 8th degree polynomial in the denominator. These factorials grow very, very rapidly. And so you could actually reason that n factorial over n to the 8th plus 1, that actually converges to infinity as n goes to infinity. And so, well, since this does not equal 0, by the nth term test, you can also see that this is going to diverge. Okay, so you could actually use the nth term test here. Let's take a look at one more example. Let's see why case 3, if the rho is equal to 1, that the ratio test fails. Let's try to see what happens there. Well, we're going to look at two series, this one and this one. Now, of course, this one diverges, that's your harmonic series, and yet this one converges. That's by the p-series test. In fact, you can use the p-series test on the first one as well. Now we're going to see that for both of these, the rho is equal to 1. So that's why if rho comes out to be 1, this test fails, because here's an example where you have a divergent series with rho equaling 1, and here you have a convergent series with rho equaling 1. So in other words, when rho is equal to 1, we have no idea what's going to happen. We're going to have to analyze the series using different methods. Let's see that we get rho equaling 1 for both of these. So for the first one, the ANs are 1 over n. So if we look at the limit, of course that's going to be and then just simplifying that, we see that we get 1, right? Okay, so in this case, we have a divergent series that diverges, and the rho came out to be 1. Now if we look at this one, our ANs are going to be 1 over n squared. And so what we're going to get then is and simplifying that, we get, and of course since the denominator is just n squared plus 2n plus 1, we see that this limit is also 1. So for both of these series, the rho came out to be 1, yet one series diverges and the other one converges. So we see why, with this example, when rho is equal to 1, the test fails. Now, of course, once you find out that the rho is 1, then you can go back and try to use some other test to determine whether you have convergence or divergence. For these two, of course, you could use the p-series test.